All right, so today what I want to do is I want to take a look at an example of where a problem looks like it's in 2 dimensions, but it's actually in 1 dimension. But we need to do some vector addition, 2-dimensional vector stuff, in order to actually properly understand what's going on. So what we're going to do in this case is we are going to start with a box on a ramp. I'm not going to write out the whole problem. I'm going to need my space here. I'm going to assume that my ramp is at a 40-degree angle, that my box starts from the top here at rest, and that that initial height is 0.5 meters. And we want to know how fast is it moving when it reaches the bottom of the ramp. So the idea with this problem is it's kinematics. So there's 2 different perspectives to take on it. So you could picture that because it moves to the right and it moves downward, that this is a 2-dimensional problem. In which case you would have an initial velocity in the x direction, which would be 0. You'd have an initial velocity in the y direction, which would be 0. And then we would have some final component of this velocity vx, and you would have another component of this velocity vy, and that those would add up to be some final velocity v. In order for this to work, you would also have to have a y displacement and an x displacement. You would have to have a y acceleration and an x acceleration. And that would be possible. It would be a lot of work. You'd have to resolve all your vectors and then solve for your vectors and then add them together again. And that's one way to do it. The other way we can solve problems like this is if I can actually rotate my coordinate axes, I can change this back into a 1-dimensional problem. So if I rotate my axes here so that my positive x-axis is parallel to the ramp and my y-axis is perpendicular to the ramp, then I have a 90-degree angle right here. Then my box only moves in the x direction. I've made it a 1-dimensional motion problem. Now, we did this already in 1D, but the big question was, what's the acceleration? So in this problem, they're giving me an initial velocity equal to 0. They're giving me an unknown final velocity. They're giving me a starting height, but that starting height is not relative to my correct directions here, but they are giving me my starting height. And I don't know time and I don't know acceleration. Well, here's the thing. If this ramp is frictionless, and this only works if it's frictionless, we can actually find the acceleration using some vector principles. Now, if this is not frictionless, then the acceleration is impossible to find without forces or some other kinematic information like time. But if we don't know time and we don't know acceleration, there isn't any way for us to figure that out, because that'd be 2 unknown kinematic variables. So here's how it works. Picture the box if it were to just fall to the ground, if it were to fall 0.5 meters and hit the ground. If it did that, its acceleration would equal -g, okay? If it fell down from a height of y equals 0.5 meters to my y equals 0 meters. So I'm defining my upward direction as positive, so my acceleration due to gravity would be negative. Gravity pulls it downward. But the problem is when I stick a ramp in there, well, I could even like have rotated the block. I could have dropped the block at that exact same angle. So if I had rotated the block, the problem is it can't fall directly down to the ground. It's trying to. Gravity is still what's trying to pull it down, but the ramp's getting in the way. And when we get to forces, we'll understand that the ramp is actually pushing in this y direction that we're defining, this positive y direction, against gravity. And that's changing the way things work. So we can actually treat this downward acceleration as a vector. And I can use my triangle to learn some information about that acceleration. So if we take that new angled coordinate system, so we have our positive x direction and our positive y direction here, then what happens is that this acceleration vector that's equal to negative g is pointing straight down. It's at an angle to my x and y coordinates. So I can find a way to break this acceleration vector into x and y components if I can make a right triangle. Well, I can make a right triangle by bringing this across here, and then that's a right triangle. And then I have this angle here that would relate my AY, which is going perpendicular to the ramp, and my AX, which is going parallel to the ramp. So I can do that. But how do I do that? How do I know what this angle theta is? Well, what's really awesome about this angle theta is it's actually 40 degrees. That angle theta is that same angle right there. And we can prove it using a little bit of geometry. So I have a 90-degree angle here between this A vector. So if I were to make this box right here, then this angle right here would be 90 minus 40, because that's a right triangle. So this angle has to be 60 degrees. Well, I also have a right triangle here. Well, actually I have a 90-degree angle right here. So I've got a 90-degree angle between my x and y axes. So that 90-degree angle between my x and y axes is made up of this orange 60 degrees and this unknown blue theta. Well, because that's 90 degrees, my theta here has to be 90 minus 60, which is just 40 degrees. So if I know the angle of my ramp, I know the angle between AX and AY. And then I could find AX. The acceleration in the horizontal direction would be my hypotenuse, which is A. And because it's the opposite side of this right triangle, it'd be A sine theta. Well, Well, that A sine theta, that A is G. So my horizontal acceleration here has a magnitude equal to G sine theta, as long as it's frictionless. So if I know the angle of the ramp, I know the acceleration on this frictionless ramp. Now, once again, if there's friction, it'll be smaller than this value, and we'll be able to see that next unit when we start learning about forces. Now, you're saying, oh, well, that's an AY. Why isn't the AY 0? Why is it there? Well, technically, there is another acceleration that is equal in magnitude, and that's, I would call it A due to the ramp. So this is the y component of the acceleration due to gravity. This is the x component of the acceleration due to gravity. This is the y component of the acceleration due to the ramp, due to the fact that the ramp is pushing up. And what we'll learn is that what the ramp is trying to do to the box is equal and opposite to this y component of the gravity. So therefore they cancel out. So the only acceleration we end up having is this x component. But really, in order to understand this, you have to understand forces. So don't get wrapped up in that, but just realize that this horizontal component, this not horizontal, but this parallel component to my ramp is the direction of motion of my box. And so that is the acceleration that is responsible for that motion in the x direction. So then if I wanted to solve this problem, I can set this up in a pure x direction. So I can define x equals 0 to be the starting point of the block. And I can define x equal to L, for right now, just call it the length of the ramp L, to be the distance there. And the acceleration in the x direction is going to be this g sine theta. So now I'm like, okay, so I know that my v in the x direction is equal to 0. I know that I'm looking for vx at the end. So I'm still missing this length L, but hey, what do you know? This is another triangle. So if I were to make a triangle here with the ramp, I have my height h and my length L. Length is the hypotenuse, h is the opposite side from 40 degrees. So the sine of my angle theta is going to be my opposite over my length, so my height over the length of that ramp, so opposite over hypotenuse. So that means the length of that ramp is going to be h over sine theta. So I do actually know that ending x value because it is h over sine theta. So if I wanted to go through, therefore, and do the kinematics for this, I can. So what happens in this case is if I look at my variable list, I need an equation that once again doesn't involve time because I don't know anything about time. Well, my kinematic equation that doesn't involve time is this equation. As it's written on the AP Physics 1 formula sheet. And at this point in time, I can go through and sub in anything that's 0. Well, my initial x direction velocity is 0. And I'm also going to start off at x0 equals 0. So I can set those equal to 0. So I get vx squared is equal to 2ax times x. Now, I already have some algebraic definitions of these, so I could sub those in. So vx squared is going to be 2 g sine theta, and L, x is L, which is h over sine theta. And so what I find is that the sine theta actually amazingly on a frictionless ramp cancels out. And I wouldn't know that if I just started plugging numbers in. And I find that my Vx is equal to 2g times h. So what this non-numerical equation tells me that just plugging in numbers wouldn't, is that my speed at the bottom depends not on the angle, but only on the height. So even if this was a really steep ramp, I would still have the same speed at the bottom. But if my ramp was steeper, so say it was a 60-degree ramp, I would have the same speed at the bottom, but it was going to take me a lot less time to get there because I'm going to have a bigger acceleration because more of my triangle for my acceleration would be there because the sine theta, the y component of that triangle would be larger. So I'd end up getting there in a shorter amount of time, but the speed at the bottom would be exactly the same. So that's what we can learn from this non-numerical equation. The big pitfall on this when people start going through and trying this on their own is I've seen some mistakes made in the triangle. So I see people try this, so they've got their ramp and they forget the g sine theta, or it's a problem and it asks you to prove that the acceleration is g sine theta. You can't just say that without like any sort of guesstimation. But what I've seen people do is make your triangle right here. Let's put that in the center. So here's my acceleration due to gravity. in terms of magnitude. The magnitude that's equal to g. And I've seen people try and make that a hypotenuse. Instead. And they put g there, and then they make their acceleration the hypotenuse right here. And they make that equal to a. And so then they instead end up with something that is different. This just graphically, you can see that this is wrong because this says that a would have to be bigger than ay, looking at that triangle. But my acceleration down the ramp cannot be bigger than my acceleration due to gravity because the ramp's getting in the way. So you have to make sure you go through the steps, rotate your axes, identify your angle, resolve your components, and all those steps that we do, because otherwise if you try and take shortcuts, you're going to end up with things that you can calculate but that don't actually make sense. So, and when we do real labs, we're going to find that our acceleration from labs tends to be much smaller in real life. So you could have, if you wanted to, go through and numerically solve this problem. We ended up with Vx is the square root of 2gh. So if we wanted to actually figure out what the speed was, we get the square root of 2 times 9.8 meters per second squared times a height of 0.5 meters. And you'd end up with a final speed of 9.9 meters per second. So the speed at the bottom would be 9.9 meters per second. So just reminders, this process only works if there's no friction. Our acceleration on a frictionless ramp is g sine theta. And the bigger theta is, the bigger theta gets, the larger the magnitude of the acceleration gets. Because if we were to look at the sine equation, if sine equals 0, if theta equals 0, sine is 0, so you'd have an acceleration of 0. If it's 90 degrees, your sine of 90 would be 1, your acceleration would be g. So basically, as my ramp goes from flat with acceleration to 0, it goes to an angle with acceleration of g sine theta. If it were perfectly vertical, your acceleration would equal g in magnitude. If the ramp was frictionless, basically the ramp isn't doing anything except for guiding it down, but not slowing it down. So there you go, motion on a ramp in 2 dimensions.